In a lot of the fields where calculus comes in handy, we want to know where a certain function is peaking or where it's at its lowest. That's what this section is all about. How do you tell where a function is at a minimum point or where it's at a maximum point? We're going to find out that derivatives can help us out with this. These highs and lows, these maximums and minimums, they're called extrema. And extrema is just a plural word for these extreme values. Looking in this box, you can see the definition of minimum and maximum. Pretty common sense, but this is a mathematical definition for it. Notice that there are several ways of denoting these minimums and maximums, but the important point is that these extrema can occur at interior points of an interval or at the endpoints if we're talking about a closed interval. More about that in just a minute. Now, a function doesn't have to have a minimum or maximum on an interval. If you look at figure 3.1a, notice we're talking about a closed interval from x equals 0 to x equals 2. Notice the closed dots. In that interval, there's a minimum at x equals 0 and a maximum where x equals 2. Looking at figure 3.1b, there's a minimum at x equals 0, but where x is 2, there's an open dot, so it doesn't have a maximum. Think about that. We can get as close to a y value of 5 as we want, but we can never reach 5. That means no maximum. For figure 3.1c, where x is 0, there's an open dot, and then the function is defined to be 2 at that point. What does that mean? Well, it means the function is not continuous at x equals 0, so there's not a minimum at that point where x is 0. But there is a maximum where x is 2. The extreme value theorem ties these examples together. Look at what the extreme value theorem is saying. As long as function f is continuous and we're talking about a closed interval, that means the endpoints have colored dots, then function f has both a minimum and a maximum on that interval. In figure 3.2, the graph has a relative maximum at x equals 0 and a relative minimum at x equals 2. These are like peaks and valleys, if you will. So you might ask yourself, how do these peaks and valleys occur in a function? One way is when the peak or valley is a smooth curve, similar to the one shown in figure 3.2. At those points, the slope of the tangent line is 0, meaning the derivative is 0 at that point. We could also have a point in the interval where there is no derivative, that is, where the function is not differentiable. Look at the definitions of relative extrema. Now, this doesn't have anything to do with your weird uncle that gets all political at family get-togethers. Instead, it reminds us that we may not know if a value is a maximum or minimum of the whole function, but only that it's a relative maximum or minimum for a certain interval. It's kind of like being the smartest kid in your math class, but not necessarily the smartest kid once you get to MIT. The potential locations of relative extrema are at x values called critical numbers. That means we've got to find out where these critical numbers are. They happen where either the derivative doesn't exist, meaning the function's not differentiable at that point, or where the derivative is 0. Theorem 3.2 tells us that each relative minimum or maximum occurs at a critical number. Make sure you see what it doesn't say. It does not say that every critical number results in a minimum or maximum. Make sure you understand the difference between those two statements. Finally, if we're talking about a closed interval, then the maximum or minimum for that interval might occur at one of the endpoints. That means these relative extrema could occur, A, where the derivative of the function is 0, if it is at any point, B, where the function is not differentiable, and C, at closed interval endpoints. That's where these guidelines come in. First, find the critical numbers of f on the interval that we're talking about. The critical numbers, once again, where the derivative is 0 or where there is no derivative. Evaluate the function at those critical numbers. So you're going to get a y value at those critical numbers. Then you're going to get a y value for the function at its endpoints for that interval. Once you've done that, then you can compare those values of f to find where the minimum and maximum values are. So let's try a couple of these. All right, our first example here, we've got f of x equals 4x squared minus 6x. To find the critical numbers, I want to find out where the derivative of this is 0. We're not talking about a closed interval here. We're just trying to find the critical numbers. So the first thing I do is find the derivative of my function. I get this, and then I set that to 0 to find out at what x value the derivative is going to be 0. I'll solve for x, and at 3/4, when x is 3/4, I know that the derivative is 0. So that means 3/4 is the single critical number for this function. Here's our function y equals 4x squared minus 6x. I'm going to superimpose the derivative function, which was a straight line like we found when we worked the problem. If we look at where the derivative function crosses the x-axis, it's at the point 3/4, which says at that point there's a critical number. And if we look on our original function, we see at that point that critical number is right here, which turns out in this case to be a minimum. That means right there at the vertex of this parabola, we'd have a tangent line with a slope of 0. Because remember, this blue line represents the derivative function. It's saying it has a 0 when x is 3/4. Understand what it's trying to tell you. To the right of that point, for the derivative line, it's saying the slopes are going in a positive direction. That's what's happening on our original function to the right of the vertex. This derivative function says to the left of 3/4, the slopes of the tangent lines are in a negative direction, which would be over here on this side. One last thing, if you thought about it back in algebra, if you'd known about it back in algebra, if you took the function of a parabola and found the derivative, it would tell you the x value of the vertex. All right, let's look at the next one. I want to find the derivative, so it's a product rule. So I multiply t times the derivative of the square root of 4 minus t, and then I multiply the square root of 4 minus t times the derivative of t, which is just 1. I clean that up a little bit. And now I've got two fractions. I want both of them over the same denominator. Well, the common denominator here is 2 times the square root of 4 minus t. So I multiply my second fraction by that, top and bottom, like this, and then multiply. And now everything's over the same denominator. I'm going to remove my parentheses. And then collect like terms. So I get negative 3t plus 8 over 2 times the square root of 4 minus t. All right, that's a rational function going on there. Back in college algebra, we said when you have a rational expression like this, to find the critical values is what we called them there. To find those, you find out where the numerator equals 0 and where the denominator equals 0. Well, it's going to be the same kind of thing for these critical numbers. So I'm going to take them one at a time. I'm going to find where the numerator equals 0. That means I solve for t, and I'm getting one of the critical numbers is where t equals 8/3. All right, so let's find where the second one is. I've set the denominator to 0, but I don't have to do the whole denominator. All I got to do is find what in that denominator would make the derivative not exist. And that's where the denominator would be 0. So all I have to do is say 4 minus t equals 0, because if that's 0, so is the whole denominator. And I get this. Where t is 4, then that would be another critical number, except for the fact that we're only searching for values of t less than 3. Go back and check. So that means the only one for the interval we're talking about that is a critical number is where t equals 8/3. Here's our function y equals t times the square root of 4 minus t. We can tell it's going to have a maximum up there. Let's superimpose the derivative function. And notice what it's telling us. It's telling us at the point 2.66, well, that number, which is 8/3, that our original function would have a critical number. If we go up to that point, we see that the maximum in this case would have a tangent line up here whose slope is 0. All right, last example. Everybody loves these trig functions. So let's mess around with this one a little bit. This is two different functions added together, so I'm going to treat them separately. So the first thing I'll do is find the derivative and remind myself, before I even do that I'm only looking for values between 0 and 2 pi. All right, so I find the derivative. Sunny's helping once more. You can hear her snoring. So I pull my constant 2 out, and I've got the derivative of secant is just secant theta tangent theta. I find the derivative of tangent theta, that's secant squared theta. I can rewrite that as this expression. Now, if I set that second expression to 0, I'm going to be finding where the derivative of that thing equals 0. I've got two things multiplied together, secant theta and 2 tan theta plus secant theta. They equal 0. That means I can set them each to 0. So I set secant theta to 0, and now I'm having to think a little bit. Secant is equal to 1 over cosine theta. Where would 1 over cosine theta ever be 0? Cosine goes from -1 to +1. No matter what value of cosine I put there, that numerator is never going to be 0. So that means this one is not going to be a possible critical number. So I go to the second one, and I set it to 0. I have to think a little bit about this one. How do I tie these two things together? And one way would be to change everything to sine and cosine. And I'm looking at those two terms, and I can pull out a 1 over cosine theta. And get this. Now remember, I'm not just looking for where the derivative is 0, I'm also looking for places where the derivative is not defined. So I'm looking at 1 over cosine theta. When would that number right there be undefined? Well, when cosine theta is 0. Where does that occur? Right here, at pi over 2 and 3 pi over 2. Now notice both of those are less than our 2 pi cutoff up there at the top. So at those 2 points, pi over 2 and 3 pi over 2, cosine theta is 0, which would make our our derivative undefined. We're talking about derivatives here. All right, so then I take the second part of that expression, 2 sine theta plus 1 equals 0. I'm not seeing anything there that would make something go undefined, so I'm going to solve for theta. Where does sine theta equal -1/2? Well, I know sine is positive in quadrants 1 and 2, so that means this has to be in quadrants 3 and 4. Now remember, the reference angle here is going to be what? For sine of 1/2, the reference angle is going to be pi over 6. So in quadrant 3, that corresponds to 7 pi over 6. And in quadrant 4, 11 pi over 6. That means we have 4 possible critical numbers. Pi over 2, 3 pi over 2, 7 pi over 6, and 11 pi over 6. We would have to test each one of those to see if it's a minimum or maximum. And that step's coming up next. But for right now, we've got 4 possible critical numbers. All right, next is our function y equals 2 secant x plus tangent x. Here's the derivative function superimposed. Now from the derivative function, we found that it crosses, the blue line crosses at 7 pi over 6 and 11 pi over 6. At those points, notice what's going on. Let me move it up a little bit. We've got a place on our original function where the tangent line has a slope of 0 right here. We have a place on our original function where the tangent line would have a slope of 0. That comes from the derivative. Now, in dealing with the cosine part of it, we realize, let's zoom out a little bit, that at pi over 2, that 1 over cosine is not defined. And at 3 pi over 2, 1 over cosine is not defined. So those were our other critical numbers, and we found 4 of them in that problem. Okay, here's our first one where we're going to find the actual extrema. That means we've got to figure out what f is at the endpoints, and we've got to see if there's any places where the derivative is 0. So the first thing we're going to do is try and find the derivative. Well, it's a polynomial, so that derivative exists everywhere. I set the derivative to 0. I can divide a 12 out and just leave this. Now what I don't want to do is start canceling out some of my x's, because I could lose possible critical numbers that way. So I'm going to factor out an x squared. Now then I've got 2 factors multiplied together that give me 0. So I take each one and I set it to 0. So that means there is one possible critical, well, there is a critical number, possibly a minimum, possibly a maximum. We don't know if it's either. I take my x minus 1, set it to 0, and so another critical number is x equals 1. All right, that's dealing with the derivative part. Now I've got to evaluate the function f, not the derivative function, but the function f at -1, one of our endpoints. So I'm just going to use synthetic division on this. And I know that f of -1 is 7. I'm going to do the same thing for the other endpoint. And I find out that f of 2 is 16. Okay, I've got my endpoints evaluated for f. Now I've got to take my 2 critical numbers that I got from the derivative and evaluate them. Now, you don't have to use synthetic division. I can just plug these values in if I want to. I could do synthetic division or just the plug-in technique, I know that f of 0 is 0. That was one of my critical numbers. I know that f of 1 is going to come out to be -1. So there are my function f evaluated at the endpoints and at the critical numbers. All I got to do now is just look at them and say, well, where's my minimum? Where's my maximum? So my minimum is obviously -1. My maximum is 16. This function is y equals 3x to the 4th minus 4x cubed. Now on this one, we were restricting our search to an interval -1 to 2. All right, so here is the derivative function. Look what it's telling us. Where the derivative function crosses the x-axis here at 0, we've got a critical number. Now, if you look at our original function, there's a tangent line going right through here. Notice its slope is 0. The derivative function crosses over here at 1 also, and that means at that point, we have another critical number, which turned out to be a minimum right here. Now, we were also dealing with our endpoints. So here's -1. I think if we go up, we'll discover that at -1, we have our maximum, in this case, of 7. And what else did we find? We found f of 1 was the minimum we just talked about. So in dealing with the endpoints and what we found from the derivative function, we could find our maximum and minimums. All right, let's give this one a try. I've got a fractional exponent here. Those are always fun. So let's get the derivative first. And then let's simplify a little bit. I can cancel those 3's, and that's going to give me this. All right, I've got, let's make it maybe even a little more approachable here. So I've got a whole number minus a fraction. Let's get them both over one common denominator. So I multiply my whole number times the cube root of x, top and bottom. And that's going to give me one numerator over the cube root of x. Okay. I want to know where the numerator is 0. So I set it to 0. I start trying to solve for x here. And where is the cube root of x? 1. Well, it's where x equals 1. So there's one of our critical numbers. Now I'm looking at the denominator. If that denominator were 0, that means my derivative function would be undefined. And that's another kind of thing I'm looking for. So where would that denominator be 0? Well, I can solve it for 0. And I get, well, when x is 0, the denominator would be 0. There's another critical number. All right, let's start solving our endpoints to see what the function of f is for our endpoints. So f of -1, now this is f of -1, not f prime of -1. Keep that in mind. So f of -1 is -5. F of 3 now think about this with me. This doesn't come out even. No nice number here. So I've got the cube root of 9. Well, I know the cube root of 9 has to be a little bigger than 2 because the cube root of 8 is 2. So I've got 3 times a number a little bigger than 2, and I'm taking that away. So that's going to mean a little bigger than 6 that I'm taking away from 6. So I know I'm getting a negative value, not a real big one. I went ahead and put it in the calculator, and I'm showing you what I got there. That's for future reference. Just hold on a second. So then I'm going to evaluate my critical numbers. So where an x is 0, my function of f is 0. And when x is 1, my y value is -1. Now I'm looking through these. The reason I needed to find out that f of 3 was that big is I'm going to compare it to -5 up above it for the minimum. So I know that -5 is smaller than my -0.24 there. So -5 is the minimum on this interval, and the maximum is 0. And here's the graph of that last one. Notice it's got a weird shape to it. This right here is called a cusp. Now then, the function's not differentiable there because the limit from the left-hand side is different from the limit from the right-hand side. So even though we can't differentiate it there, it doesn't have a derivative, it can still be a critical number. And so it is, as we found out in our calculations. Let's put the derivative function on. Notice it crosses the x-axis at 1, and at that point, we have a critical number, which turns out to be this minimum right here. Over here at 3, which is one of the endpoints we looked at, that's where the value was at 0.24. Then we found another critical number at -1, our other endpoint, and we came down and that turned out to be -5, which was our minimum. And what would this set of notes be without one more trig function? So let's take a look at this. Okay, let's find the derivative. Okay, not too bad. I can get rid of those negative signs. And let's stop right here a second. I'm seeing x for my first term, cosine x, and I'm seeing sine of 2x for my second. Those are two different things. I can't compare or work with sine of 2x and cosine of x and get anything that's going to help me. So what I did was I went back to the double-angled formulas in trig, and I found out that the sine of 2x I can convert into 2 times the sine x cosine x. Comes in handy here. Okay, let's start trying to find out where this derivative is 0. What have I got here? I don't want to cancel anything out, but I can factor something out. Okay, so I've got cosine x times 1 plus 2 sine x equals 0. I've got two factors, and when I multiply them together, I get 0. So I set each one to 0. Where is cosine x 0? Now remember, we're restricting this closed interval to 0 to 2 pi. In that interval, where is cosine x 0? Well, at these two places. All right, let's find out about 1 plus 2 sine x. I'll solve this for x. And we've kind of seen this before. This is true at 7 pi over 6 and 11 pi over 6. So I've got 4 critical numbers here, just based on the derivative. Now then I have to worry about the endpoints. So I'm going to evaluate this function at 0. And so f evaluated at 0 is -1. Let's try the other endpoint. F evaluated at 2 pi on the other hand. Now notice out here I put cosine of 4 pi because it's 2 times whatever that x value is. I'm getting -1. Now I have to take each one of those 4 critical numbers and evaluate f at those. So here's pi over 2. Again, multiplying what's inside the cosine by 2, and I'm getting the function is, the y value of the function is 3 there. 7 pi over 6. I'm getting -3/2. So -1.5 at 3 pi over 2. Getting -1 at 11 pi over 6. I'm getting -1.5. So I'm scanning back through those. I'm getting 2 values of -1. But in terms of a minimum, the minimum is -3/2. And for a maximum, that's pretty easy. That's at 3. All right, here is our function y equals 2 sine x minus cosine of 2x. Lots of hills and valleys in this one. Here's our derivative function. Notice where the derivative function is crossing the x-axis. Again, that's where the slope at a point on the original function, the slope is 0. So at pi over 2, 7 pi over 6, and this is what we found when we did the math, 3 pi over 2, 11 pi over 6, and then that gets us out here to 2 pi, which was the end of our interval. Look what corresponds for pi over 2. Up here on our original function, there would be a tangent line with a slope of 0. At 7 pi over 6, tangent line with a slope of 0. Same way for each time that that derivative function crosses the x-axis. You're seeing that. So we evaluated the original function at all of those points, and then we evaluated it at 0, and that's how we got the -1 here, and we evaluated it at 2 pi, where we got this other -1. As it turns out, we had some values lower than that for our minimums, and then we had this value of 3 up here for our maximum. So that's the process we have to go through to find these extrema. To recap, what do? We find the derivative, we set it to 0, we find out what values of x give us that 0. Those are our critical numbers. We also find out what values of x make that function non-differentiable. Those are critical numbers too. Then we evaluate all of those values, including the endpoints. We run them back through the function f. Then we look at the final values like we did here and realize where our minimums and maximums are.